Hi, it's Mike Barnes here again. This time to talk to you about the difference between power and energy. Do you know that most folks don't realize that there is a difference between power and energy? And so they use these two terms interchangeably. But there is a big difference between these two words. And you really have to understand the difference between power and energy to get a true handle on solar generation as well as electrical principles in general. So what I've used here to get us started is the image of a simple water faucet. Now, electricity doesn't work exactly like water flowing from a faucet, but we can look at some of the elements of flowing water to help us simplify how electricity works and to get a better understanding of what electrical terms are. So let's begin with the first term on my diagram here labeled pressure. Let's say you have this water faucet outside of your house and you want to wash your car. If I turn the handle on the faucet, water flows out because it exists right behind the valve under pressure, measured in pounds per square inch. So let's assume we have 20 psi, pounds per square inch, of water pressure behind the valve. In the electrical analogy, this would be referred to as voltage. So like water pressure, you might think of voltage as electrical pressure. The more we have, the more electricity flows. So let's put the term volts right here under pressure. Next, we have the actual water flow, and again, we can use this analogy for the electrical term amps. Using our water example, when we refer to flow, you can think of amperage the same way as the flow of electrons past a point. So let's put the term amps under our water example, flow. Now in the water example, we need both water pressure and water flow to have water power. And so I'll label that here as power. Think about it. If we wanted to use a pressure washer to get the grime off our car, we could take the 20 psi water supply from the faucet on our house, hook it up to a pressure washer, and actually get 2,500 pounds per square inch of pressure. So let's erase the 20 psi and change it to electrical pressure. With electricity, if we crank up the electrical pressure, the voltage, to say 240 volts through the use of a transformer, which I'll talk about in another video, we will have more electrical power labeled here on my drawing. In electrical terms, when you multiply electrical pressure in volts times electrical flow in amps, you get power, and that's measured in watts. Now finally, at the bottom of my illustration, we're going to draw a bucket of water. Here's where the electrical analogies have to make a stretch, because other than in batteries and some other electrical storage devices, we really don't store energy in a bucket. Instead, we use the energy every day when we need it in real time. But the electric company has to have a way to charge us for the power we use over time. That's energy. You see, another way of saying this then is that energy is power times time. Now, if we accumulate power in, say, a rechargeable battery, that's a form of stored energy, like the bucket of water in our drawing. We use the term amp hours to express DC energy, DC standing for direct current. Back to our drawing then, we use the term watt hours to measure AC energy. That is AC standing for alternating current. Now this all comes together in what's called Ohm's law, which we're going to discuss next. You see, electricity happens to be very mathematical, so we have a basic formula we can use to determine how much power we have. I call it the pi formula because it's as easy as pi to remember. Here's how it works. Way back when electricity was just being discovered, no one really knew what it was, but they knew it had some measurable properties, like just how badly you got shocked, for example. Now, as each one of these electrical properties were measured by various scientists, they took on new names to reflect their discoverers. The P in PIE or pi stands for power, but we use the term watts as a power measurement because this dude, James Watt, an instrument maker, was able to measure power, and so he used his name, the watt, as a unit of power measurement. How convenient. Now, the I part of our pi formula stands for the term intensity. Have you ever gotten shocked? If so, you probably remember how intense the shock was. If you put your tongue on the positive and negative poles of a standard 9-volt DC battery, those are the small rectangular ones, you'll definitely feel a serious tingle if it's fully charged. Now, the discoverer in this case was André Marie Ampère, a French mathematician and physicist who's also considered the father of electrodynamics. Well, he takes credit for the measurement of electrical flow. So he got to name it too. That's how the flow of intensity gets called the ampere, but it's often shortened to amps or simply amp if it's singular. Next we have the volt. Once again, back in the day, scientists knew that there was a force behind electricity, and so it was termed electromotive force, the E in the pi formula. Then an Italian physicist, Alessandro Volta, who probably invented the chemical battery, measured this electromotive force and called it, you guessed it, the volt. I think there's a car now that bears his name. Well, with all of these discoverers and their various names and letters, it makes this Ohm's law formula confusing because the measurement letters don't line up with the original words. Instead, power, P, is equal to watts, W. Intensity, I, is equal to amps, which is the A, and electromotive force, the E in pi, is equal to volts, or V. So let's try to put this all together to figure out power. Since P is equal to IE, then watts is equal to amps times volts. To use an easy example, let's say you have a toaster that's 1200 watts and you plug it into a 120 volt outlet like you have in your kitchen. To find the amount of current in the toaster, we will use this equation. 1200 watts is equal to I times 120 volts. When you use the toaster, it's going to draw or demand 10 amps of current to flow. We're trying to find the value of I, so we use algebra and divide both sides of the equation by 120 volts. And we find that I is equal to 10 amps of electrical current. In other words, your 1200 watt toaster plugged into a standard 120 volt electrical outlet will draw or demand 10 amps of current to flow. Okay, so that's power, but what about energy? The toaster is rated at 1200 watts. That's how powerful it is. Just like a car engine. If I told you that my car has a 400 horsepower engine, it doesn't, but let's just say it did, that's 400 horsepower, you would have an idea that this is quite a powerful car. But that doesn't really tell you anything about the energy the car must use to move. See, you've actually got to drive the car to determine how much energy it uses, just like you have to use the toaster to figure out how much energy it uses. You see, the power rating of a car or a toaster is simply a snapshot, like taking a picture. Power is a picture of what something can do. On the other hand, energy is like a movie. Energy is what a device or machine is actually using while it's working. For example, you're watching this video right now, and the device you're watching it on is using energy to play the movie. If you turn off your laptop, your iPad, or smartphone, you'll notice somewhere on the device or in the software that it has a power rating measured in watts. But you're not going to know how much it costs you to use the energy for the device until you take its power rating and multiply it times the hours you are using it. You see, the difference between power and energy, and here's the kicker, it's time. Okay, so to sum it all up, watts, which is a power measurement, times time in hours is equal to energy. So you must take the power rating, a snapshot of what something can do in watts, times the amount of time in hours to come up with the energy that it uses. When we do that in our energy formula here, we multiply power times hours to come up with watt hours. And conveniently, this is how the electric company bills us to use electricity. They simply measure energy in chunks of 1,000 watt hours at a time, called a kilowatt hour, and we get charged for that. So in the final equation, take watt hours and divide by 1,000, or move the decimal point 3 places to the left, and you've got kilowatt hours. Well, I sure hope you've had as much fun watching this video as I've had recording it. And I hope this presentation has helped you in your understanding of the difference between power and energy. By the way, the videos are available to be seen on YouTube, Vimeo, and D2L. And as a teaser for another video, we really didn't talk about resistance, another Ohm's law measurement. In fact, Ohm took his own name for this measurement. But let's talk about that in another video. In the meantime, may God bless your day, and I hope to see you again soon.